Good morning, welcome to EduSet Network. Friend, as you know, we are having discussion on computer science and precise topic is wireless network. So far we have understood the fundamentals and LAN, WAN and MAN, and we will continue our discussion. We will try to understand the details of it. And for discussion on this very topic, we have in the studio the same resource person, Dr. D.K. Lobial. He teaches computer science in Jawaharlal Nehru University, and you have already heard the lecture, previous lecture, so you will certainly get benefit what the wireless network and how does it work. So on your behalf, I welcome him for the recent lecture on this topic. Welcome, sir.
Thank you, Amarenji. We started with wireless network, and yesterday we stopped at a point where we have been discussing 802.11. That is part of wireless LAN, and gradually today I will end with this, and tomorrow we will begin with wireless WAN, where special focus will be on cellular network tomorrow onwards. But today I will continue where I left yesterday. The reason behind having two lectures on 802.11 is that this is one of the most widely used MAC layer protocol or wireless card in wireless LANs. So that is why it needs a detailed discussion, and where we left yesterday was it seems to be a half discussion, therefore I would like to continue with this. Now where I left yesterday, I will begin from that point, and I was here now yesterday. So what we talked yesterday is that this N02.11, it works in asynchronous data service DCF, where it uses CSMA CA and uses RTS CTS mechanism for what you call virtual carrier sensing as well as collision avoidance. And the second kind of service which we talked about is a time bounded service, that is polling. It is an optional portion which we will see little later, but in a time constrained service like real time service, you cannot wait for a random period of time because delay is a very important constraint. So therefore you need a time bound service. So that is where we will use PCF. And whether you use PCF or you use DCF, one of the important notion where we stopped yesterday was that the interframe space, that means between two frames, whether it is a control frame like RTS CTS or a data frame, there must be gap between, because they cannot immediately, a frame cannot go immediately after another frame. That is why there is some frame space, that is what we call interframe spacing. And we discussed about three in hurry, basically DIFS and then PIFS and then SIFS. DIFS stands for DCF, D stands for DCF and IFS stands for interframe spacing. So there is a DCF interframe spacing which will work only when DCF mode is working. Then we have PIFS, that is PCF, point coordination function interframe spacing, and this will work only when it is working in PCF mode. And then we have SIFS, that is short, S stands for short, then IFS interframe spacing, that means that is the shortest period which will occur between any two frames. Now this may be useful in both the cases, whether the system is working in DCF mode or it is working on PCF mode. Now this is because we have to set priority at some point where we need that some frames, short frames must be having priority over some long frames, or I could say that the acknowledgement must have a priority over what you call data frame. That means when one station is willing to send data, other is willing to send acknowledgement, that means the station which is ready for transmission of acknowledgement must have received a data frame, and therefore it must get priority over the other data frames, so that the sender gets acknowledgement for its transmission. That is the idea. That is why it is the shortest frame. And if you look at DIFS period is the largest one, and PIFS is smaller than DIFS. That means the real time services where PIFS is used and point coordination function is used will have priority over DIFS, which is for asynchronous or data transmission. And then SIFS is smaller than PIFS because this is used for to keep a smaller gap for higher priority communication. So, we have DIFS largest, then PIFS, then SIFS. One of this interframe spacing which I have not talked is EIFS. E stands for extended interframe spacing, that is used for specific cases, but that will be the largest. That means EIFS will be larger than DIFS. Now, let us, so I left at this node and let us look at this diagram, how the layering of 802.11 works. So, if you look at this 802.1 is a logical link control, it occurs irrespective of whether you have 802.11, you have 802.3 or you have any other MAC layer protocol. So, 802.1 is a logical link control which will be almost common between your MAC and your network layer. So, that is not part of basically 802.11, I will not focus it. If you look at this, then you have PCF and below it there is a DCF. PCF is used for contention free service. The moment I say contention free service, that means for a real time service you cannot have been looking for contention by two stations which are willing to transmit at the same time. That means a station first will have a dedicated time period in which that station will be transmitting only, the others will not contend. So, there is no contention resolution. So, it is a free period. So, that is suitable for real time transmission of data. That is why it is optional, because all services are not real time services and therefore, you do not need to have system working in PCF mode all the time. Whereas, DCF is important because it's work for asynchronous as well as non real time service. So, DCF is a mandatory part and PCF is optional if you look at this, and below this we have physical layer. It is working that 802.11 using FHSS, which stands for frequency hopping spread spectrum, and then DSS direct sequence spread spectrum. Then we have infrared, and then we have DSS again for 802.11a. Then we have OFDM, orthogonal frequency division multiplexes. Then we have DSS. Now, that means it is important in a wireless system at the physical layer level that the security is very, very important. The reason is they work in an open system where anybody probably can snoop or may interrupt your signals. So, therefore, even if one peeps in or takes a signal, should not be able to decipher the message. So, the physical level security is very, very important. So, either you may be using FHSS, frequency hopping spread sequence, that means the message or the signal will not be all the time delivered on one frequency. So, you have a sequence of frequencies, that is a spectrum has spread, then which you are using a large range of frequencies. So, that is what the spread spectrum is, and then signal will keep on hopping from one frequency to another frequency. That means, if signal A is sent on frequency X, then the signal 2 will be sent on frequency Y and then frequency Z, so and so forth, and that is a random sequence. So, one cannot judge that on which frequency the signal is coming. That is how you provide security through frequency hopping spread spectrum. And then DSS uses with direct encoding the signal by applying some code. If the others, the receiving end knows the code, then only they will be able to decipher what message is being carried by the signal. So, in addition to these electromagnetic signals, one can use infrared for communication and so forth. Now, the kind of frequency band used, FHSS in 802.11, it uses 2.4 gigahertz and using frequency shift keying because it is a digital communication and modulation, and DSS also uses 2.4 in case of 802.11, and infrared also falls, and they use different kind of modulation FSK, PSK or PPM, and then the rate of data transmission is 1 or 2 Mbps. That is what the limitation is. Then there is N0 2.11a, which uses OFDM technique, and it uses the band of 5.725 gigahertz, and it uses PSK or QAM modulation, quadrature amplitude modulation, which is a mix or combination of PSK and ASK, that is amplitude shift keying and phase shift keying. It is combination of these two, so that you get more number of combinations and to get a higher bit rate. And then it provides you 6 to 54 Mbps. It may have 6, 12, 18, 24, 36, probably 48 and 54. The different data rates are suggested for this, and right, and then you have N0 2.11b, which uses direct sequence spread spectrum DSSS, and it works at 2.4 gigahertz and uses PSK for modulation and provides you a data rate of 5.5 or 11 Mbps. Now, you have G, N0 2.11g, which is most commonly used nowadays in a small area network. It uses OFDM, that is orthogonal frequency division multiplexers. That means the norm of two frequency must be 0, that is what they are orthogonal, and then it works on 2.4 gigahertz band, and it uses different kind of modulations. That means it does not stuck either to FSK or PSK or PPM and so on and so forth. It may have a variation, it may use GSK, Gaussian shift keying as well, and it provides you a data rate of 22 megahertz as well as megabits per second as well as 54 megabits per second. So, this is how the different techniques at the physical layer level, working on different frequency band and using different modulation techniques and providing you different data rate. Now, one of the thing which I told is that they use a free license band, that is what you call ISM band, industry, scientific and medical band. So, 2.4 gigahertz as well as 5.7 gigahertz bands, they both fall in ISM band and one can use them. Now, what we have been talking about is how RTS CTS mechanism work, and what we said is a station which is ready with the data and first physically sends the carrier, that is what we talked, and if it finds that the carrier is not busy, then it will grab the channel and try to send in normal case, but if the channel is busy it has to wait for some time. Now, in case of RTS CTS mechanism, it N0 2.11, after having a physical carrier sensing, that means physically sensing the carrier whether some signal is on the carrier or not. If it did not find, then it has to send an RTS for virtual carrier sensing, and if the receiver receives, then it sends. So, there is an algorithm how RTS CTS mechanism work. So, in the beginning, a station which is ready after physically sensing the carrier, what it does, if it finds carrier free, it does not immediately transmit any data. What it does, it sets its back off timer at 0 and then keep on persistently sensing, that is what is called persistent carrier sensing, and then it waits for DIFS period of time before sending RTS. Now, after waiting for DIFS period of time, then it will send its RTS frame, and after sending this RTS frame, it again sends its timer and waiting for a CTS from the receiver. Now, it sets a timer because it knows that the CTS from a receiver must come within a time limit. That means, if the CTS does not arrive and the timer set after sending RTS expires, that it will come to know there is a problem with the RTS frame which has been transmitted. That is why the CTS has not been received within the period of the timer. So, the timer, that means the moment, now there is a situation that CTS is received before the timer is out, or it may not be received at all and the timer is out, two conditions. So, therefore, the moment it receives CTS before the timer is off, then it again waits for that the receiver receives the CTS, the receiver received RTS, and then it probably, after waiting for some SIFS period of time, the receiver will send CTS. If it finds that there is no collision at the receiver, only then it will send CTS. Assume that there is no collision at the receiver, and after waiting for SIFS period of time, the receiver transmits CTS. And when the sender receives this CTS and waits for, then it waits for SIFS period of time, because it knows that it has received CTS before expiry of its timer, and it must wait for SIFS period of time. Then only after that it will send its data frame, and by setting a timer also, because it has to receive acknowledgement for the data frame before the timer expires. Now, it may receive an ACK, then your data transmission is clear. Now, the important point which is very needed here to discuss is now why in N0 2.11 it waits either for DIFS period of time or SIFS period of time, whereas in case of N0 2.11 N0 2.3 it does not happen. It immediately after sensing the carrier it transmits, and here after finding a CTS, why does the system not transmit the data immediately? Now, there are two reasons now. Is why a system waits for DIFS period of time. Now, not only that, after waiting for DIFS period of time, before transmission of data, the system at times also backs off. Why it happens so? One, assume that two stations now waiting for or sense the carrier, and both of them finds that the carrier is busy physically. Then they have to wait for some time, and then they will again sense the carrier, and they will persistently sense the carrier. That is why it is persistent CSMA, and then the moment the ongoing transmission is over or the system becomes free, the channel becomes free, then they will grab the channel. Now, here if both of them transmits at the same time, then what will happen is that both find the channel is free at the same time and both will transmit at the same time, then there will be collision, guaranteed collision. So, therefore, what is to be done? Then both the system has to wait for some time. Now, if they wait for the same time, again there will be a problem. Now, when you are in collision mode, that means when you are waiting for a DIFS period of time, and the DIFS of both systems will also expire at the same time. So, therefore, in case if the system has encountered a collision once, so therefore, there is a possibility of collision after waiting for DIFS period of time, because it deferred its transmission because somebody else was transmitting. So, at the moment when the transmission of some station is over, then it must immediately wait for some DIFS period of time. So, more than one station which have been waiting for completion of the ongoing transmission will find channel free at the same time, and then both of them will be waiting for DIFS period of time after expiry of after getting the channel free. Now, their DIFS period of time will also expire at the same time, because this is a fixed period of time. Then therefore, they must, before transmission, they must back off for a random duration, so that at any point of time you will try to avoid that in the beginning any two stations will avoid collision of their packets. Now, after DIFS period of time, they are waiting for some duration, again a random period of time. Now, one of the important factor here is that they wait for a certain random period, that means the stations goes in backup mode. When they goes in backup mode, so they are going in a waiting period of random period of waiting time. Now, their timers keeps on decrementing after a time slot. So, if the timer counter is set to 3, so it will come to 2, then it will come to 1, then it will come to 0. The moment it comes to 0, the station is free to transmit. Assume one station has set its counter to 3, sorry, other has set it to 2. So, it is well known that the system which has set its counter to 2, it will expire faster, its timer will expire faster, but at the same time that the system must also check that during the backup period that whether some transmission is also going on or not in the channel. So, a system A which has gone to backoff mode and decrementing its counter after every time slot, before decrementing its counter it must check whether there is an ongoing transmission in the channel or not, because the moment A goes on backoff, somebody else may start transmitting. So, what happens is, if the station is sensing the channel while it is in backoff mode, that means what I am saying is, even in the backoff mode, a station persistently checks the carrier whether carrier is busy or not. So, during backoff period, if it finds that the carrier is busy, so what does it do? It freezes its timer, that means the timer will not move, it will stop where it was, and the timer decrements only during a period when the channel is free. That means what? Why it is so? If the timer keeps on decrementing even during the busy period of the channel, then what will happen is, station which is in the backoff mode will keep on decrementing its backoff counter, and the moment the backoff counter reaches at 0, that and the station becomes free to transmit, it may happen that the counter has become 0, but the channel is not free or channel is busy. So, therefore, channel is busy and station A timer has become 0, now it is free to transmit, and if it transmits, then definitely there will be collision. So, therefore, it is very important the timer must decrement, backoff timer must decrement only during the period when the channel is free. So, that means during backoff it keeps on sensing the channel, and when channel is free for a slot period, then only backup timer is decremented. If again the channel becomes busy, the timer is freezed, it will not move. Again station will keep on sensing, again it will find channel free for a slot, then again it will decrement the counter. Now, that this guarantees that when the backoff timer after decrement comes to 0, it is guaranteed that the station will find that the channel is free. Therefore, it will be able to transmit and it will avoid collision. And since each station is waiting for a random period of time, going in a backup mode for a random period of time, therefore, it is very less likely that their random period will be same. So, therefore, they will not find channel free at the same time. Now, if two stations are in backup mode, one goes a timer set at 4, other timer sets at 2, and they keep on decrementing, and the station whose timer is set as 2 will decrement after 2 free slots, and now it is free to transmit. And in the meantime, the station which set its backup counter as 4 might also have decremented its counter for 2 free slots, it has reached to 2. So, its timer is at 2, and one's timer is station A's timer has reached to 0, and station B's timer is at 2. Now, station A will start transmitting. Now, station B will find that the channel is busy, therefore, it will stop its timer from decrementing. So, its timer will remain at 2 because the channel has become free. After that, after completion of transmission of A, when the channel becomes free for a slot, then B will decrement it by 1. So, it will come to 1, and again for one free slot it will decrement it to 0, then only it will be transmitting. So, at any point of time, until unless the backoff periods are not same, that when the timer reaches to 0, it is guaranteed that the station will find the channel free and it will be able to transmit. Now, so that is what, if you look at, that means when an RTS is transmitted after DIFS period of time and the receiver is waiting for SIFS period of time, then it transmits CTS. After receiving CTS, the sender will wait for SIFS period of time, then it transmits data and so on and so forth. That is how the communication between two stations is complete. But at the same time, the other stations which are not engaged in transmission, because at any given point of time only two stations can transmit. So, others will set their NAV. NAV means network activation vector, and that means each station will set its vector that how much time the ongoing transmission will take place, so that it can also knows that when they decrement the timer, and that is how it will happen. So, NAV is important for others because they have to set that they will not do any carrier sensing during this period. They know that they have to wait for this period, no carrier sensing. So, others will stop and wait for some time. That is what the NAV is. Now, so what we have been talking about is that there is a contention free period and there is a contention period. Now, when two stations contend. Now, when we are working on PCF mode, now how can it happen that the stations will know that whether the station is working in PCF mode or it is working in DCF mode, or the stations can work in both modes simultaneously. Some may work in PCF mode and some stations may work in DCF mode. Now, when that is happening, if you look at this diagram, so there is a repetition period, that what you call a cycle you can call, and the total repetition period on the top consists of two sub periods. One is contention free period followed by a contention period. So, during contention free period PCF mode will work, and during contention period DCF mode will work. Now, during this contention free period, now if you look at this diagram, there is a PIFS period of time. That means a station which is working on PCF mode will work, it will wait for PIFS period of time before sending a B frame. B stands for beacon frame, and which will see whether this is useful, whether some node is joining the network, some node is leaving the network, and whether synchronization has to be maintained or not, and therefore and whether the node you are transmitting is on or not, or is available in the network. So, therefore, these beacon periods are beacon packets are transmitted. So, after PIFS period is over, a beacon frame is transmitted to check the status of the network. After that, a station will wait for SIFS period of time. That means we have our access point. So, PCF mode is generally working on your access point. So, access point, before doing its polling, so it transmits beacon frame to check whether some new node has joined the basic service set or not, because when a node comes it has to join the basic service set, and that is being controlled by your access point. So, the access point is sending a beacon frame which it may get a response and knows that how many nodes are there in the BSS, and after that it waits for SIFS period of time. When this SIFS period is over, it will send a special frame called pole frame. That is what I talked yesterday, and with this pole frame it may be targeting this pole frame to a station 1, whether station 1 has some data to transmit or not. So, what happens? This pole frame goes to station 1, say station 1 after waiting for SIFS period of time will send yes, I am ready for the acknowledgement, it will send acknowledgement that I have data to transmit, but it is not that it will send poll, then the station will say yes, then it will say send data, then it will send data. It is not a 4-way kind of thing, that send poll, get acknowledgement, then request for, then say allow the station to transmit data, then station will transmit data, then it is not like this. So, what is happening here is the moment an access point transmits a poll frame to a station, if the target station is ready with the data, then target station sends acknowledgement for the polled frame as well as it will transmit data along with the ACK. That is what a piggybacking means. So, to save time, generally in networks piggybacking is applied, that means the ACK, the acknowledgement will be piggybacked on the data. So, the acknowledgement for the polled frame and data are combined together and make one frame and then transmitted to the access point for further delivery of the data to the target station. And after this happens, then the AP or access point will wait for SIFS period of time, and after this it will send ACK as well as polling message. ACK for that it has received the data. So, it is sending the polling message, and this polling frame will be received by all basically, and it is because it is a broadcast medium. And the station A1 which transmitted earlier data will see there is an acknowledgement for it that its data has gone correctly, and the other station now which is being polled, maybe station 2, will also receive it and it knows that it is being polled for it. So, both station 1 which has been polled and transmitted its data, for this the acknowledgement, and for station B the poll frame are coming together simultaneously at the same time in one frame. So, it is saving time, then station 2 will do the same and so on and so forth. And after that this contention free period will end, and then contention period will be starting, and the stations which are working in contention mode or DCF mode, they will start working also, because here why the contention period starts before the contention period begins before the contention period. The reason is that the PCF or the contention free communication is done for real time services which must have higher priority than non real time services. That is what the reason is. Now, this is what I showed in another way how it happens, RTS CTS, probably it is not required here. Now, in wireless LAN, it also at times the data frame is divided into fragments rather than one data frame is sent in one go. It may happen, or the frames, the data is divided into fragments, probably you call them frames. The reason is because the wireless LAN have a high bit error rate. The reason is wireless channels are always prone to errors because they are open medium, and so if the error rate is high, to avoid that the data must be fragments and small fragments must be transmitted, and the reason is smaller the fragment, the additional bits you need will be smaller, and second is each frame which has an error you can retransmit it. So, the probability of erroneous frame is much higher for wireless link than in case of wired links. So, therefore, it is always better to divide into smaller frames, smaller fragments and send them. If the fragment has an error, only you need to retransmit the small fragment. Probably it may happen that out of a frame, a big packet, only one small frame in the middle may have an error, and only you retransmit that. If you do not divide into frames, then the entire large message has to be retransmitted even if there is an error in a single bit. So, if you have a data size of, say for example 64 kbps or kilobytes, and if single bit has an error, then all 64 kilobytes have to be retransmitted. It is not a feasible way which will only cost in delay in the network. So, therefore, what is to be done is that 64 kilobytes probably may be divided into small 2000 bytes, and only if there is an error in a bit, this error may be happen in any fragment of 2000 bytes, and only that 2000 bytes needs to be retransmitted. So, by dividing into fragments, you are reducing the retransmission time or the delay occurring in the frame transmission. So, that is why wireless follows dividing frames into fragments and transmitting. So, the frames are divided into fragments, and that is why the fragmentation reduces the frame error rate, right. The error rate will increase if you have a larger frame size. And look at this, what is happening. That means, after sending this RTS, and if it receives a CTS, then it keeps on sending fragments one after another. Now, now let us look at the frame format of A0 2.11 and how does it work. Now, if you look at one of the field of this frame format is frame control field, which is 2 byte. Then there is a field D, which is called a duration field, which is 2 byte, and there are 4 address fields, each consist of 6 bytes, address 1, address 2, address 3, address 4. Definitely there may be a question coming to the minds of the student in that case, is that we have one sending station, we have one receiving station, probably 2 addresses could have been sufficient, but that is not the case here. We have 4 address fields given in the frame, address 1, address 2, address 3 and address 4. Why 4 address? That I will explain little later, but each 6 bytes, so this constitutes to 6 into 4, 24 bytes. And there is a sequence control field in the middle, that means it must contain the sequence number of a frame or the fragment, so and so forth. Then frame body, that means the data, and that may consist of 0 to the data size, maybe maximum size is 2312, and that means large size data is divided into frames of data of 2312 bytes, and definitely the large frame may have smaller size data, because the data or the message which you are transmitting may not be exact multiple of 2312. So, the last one may have lesser data, and last one is the frame sequence check, is the field used to store additional bits to be used for check the error, to detect the errors, and probably if need arises correct errors. So, this is basically in 802.11 it is for error detection, and based on this, if the frame is received, it will look at FCS field and use it to check whether there is a error, detect error, whether there is a error in the frame or not. If there is no error in the frame, it is all right, it will send positive acknowledgement. If there is error, it will a negative acknowledgement or a missing acknowledgement, and based on which the sender will retransmit the same frame. So, this is for error detection field. Now, this frame control field, if you look at, which is of 2 byte, again has certain fields further divided into subfields. So, it has a protocol version of 2 bits, because 2 bytes is 16 bit, and 16 bit as divided into 2 bit version number of the frame format. So, this it may be version 0 right now, and it may be you keep on improving and the fields changing, and therefore, the version keep on changing, and the sender and the receiver should have a same version for compatibility reasons. So, therefore, the version number of the protocol must be mentioned in the frame control field in 2 bits. So, 2 bits means 4 different versions may be applicable. And then type, the type subfield in the frame control will tell whether the frame being transmitted is a control frame, that is RTS CTS, or is a or ACK, that is also control frame, or it is a data frame which carries the data of the user, or probably at times it may be a management frame which will look the management of the network, it may be a polling frame, so and so forth. So, you have basically control frame, data frame, and so on and so forth. And there is a subtype which is again 4 bit. If you say it is control, the type of the data is controlled, that means whether you are transmitting RTS or it is carrying CTS or it is carrying ACK. So, in a control type of data, again it is either RTS or CTS, there is a subtype. So, subtype is again further categorizing the type of the data which the frame is carrying. Then there is a one bit field called 2DS and another one bit field is called 2 or from DS, and DS here stands for distribution system. Take a case when you have a basic service set, which you talked about yesterday, that you have an access point and you have certain mobile stations connected with this access point. Assume that this room has an access point, as yesterday I said the same, and then you have certain laptops and PDAs connected to this access point. The other room, little far away from here, not very far, also has an access point, because this access point is not able to control or cover all the laptops, all the person using laptops in the entire building, because this may be only covering the users in this room. So, therefore, in some other room probably you need other access point, and there is a different set of laptops and PDAs used by people now. But to have communication, these two APs are connected and then it forms extended service set, and then the connectivity. Now, how these two access points are connected? Are they connected through a switch or they are bridged together? So, there may be different way of connecting them together. Now, how these access point, two stations or two APs are connected, that is called your distribution system. So, a distribution system is referring to a backbone where two access points or multiple access points will communicate through. So, now that means it is helping you the 2DS or 2 distribution system or from distribution system, because it may happen that the sending station, mobile station or station, and the receiving station both may be connected to the same access point. That means both are part of the basic service set, this is one. And second may be no, the sender is part of access point 1 and receiver is part of access point 2. That means the receiver and senders are in different basic service set. That means the extended service set is here, in which both receiver and sender are, though they are in different basic service set. Now, so therefore, and in addition to that, we may have more service sets. So, it must know that from which distribution system the data frame or the frame is coming, or to which distribution system the frame is going. So, then what we said is we have divided the frame into fragments for better frame error rate or to control the frame error rate. So, now when one frame goes and it will be followed by the next stream of frames, therefore, it must know that when a frame goes, it must also carry the information whether the more frames are to be followed or no, not. So, the more flag contains bit 1, if more fragments to be followed, it contains 0 if it is last fragment of the frame. So, that the receiver knows if it is 0, the more flag field is 0, the receiver will know that no fragments are following. If it is 1, it knows that more fragments will come, and then retry. If the frame transmission fails, it may also attempt a retry. It is a retry attempt. So, if bit is 1, it is retry attempt, 0 no. And then power management is equally important in case of 802.11. Reason is, since your devices, mobile devices or these work on battery, and battery has to be recharged, you can't have a very large battery, you can't carry from one place to another place. So, your portable devices work on small size batteries, so that they remain portable, and the battery size small means you need to recharge is more frequently. Smaller the size, more frequent recharging you need, and therefore, you need to use, once you charge, you need to use this battery as longer as possible. So, therefore, the power saving is equally important. So, whether your device is working in power management mode or not. So, this field is 1, it is working on power management mode, and if it is 0, not. Now, this power management means some nodes which are currently not engaged either in receiving or sending of data may put off their transmitters, and therefore, if they put off their transmitters, they will save their power. The reason is, if they are not engaged in transmission, if their transmitters are on, they will have overhearing. That means, in a broadcast medium, when I speak from here, anybody sitting in this room will be hearing what I am talking, because it is a broadcast, whether one likes it or does not like it, and one will hear it because it is broadcast. Same happens there. If a station A is transmitting to station B, the all other stations which are within the range of A will be hearing it. That is what we call it overhearing. It is not intended for C, but still C is hearing it. And hearing means when it receives it, it is also consuming power in this. So, it is unnecessarily wasting its power. Second is, even if a station is neither in transmitting or nor engaged in receiving, it is in doze mode or simple mode, and it will also have some power dissipation. So, ultimately, if you add up this, all power will accumulate. If you accumulate them or add them up, then you will find there is a power loss, and to save this power, it is better to switch them off. And then if you switch them off, that means if a station is powered off, a station D, say for example, is powered off, and station A sends a message to D, then what will happen to that message? A frame, because D is off, it is not in position to listen to it, and these stations which are put off their transmitters, they also periodically wakes up. It is not put off forever. So, there is a period set how long a station has to go to sleep mode, that is also called sleep mode, and when it will wake up. So, that duration is fixed. So, a station which has gone to sleep mode or put off its or switched off its transmitter will, after expiry of the period, will again wake up or put on its transmitter. So, by the time in between, if a message comes, what will happen? So, therefore, the access point has to play an additional role of having additional buffer to store the messages of those or the data of those nodes which are in sleep mode, so that the access point can deliver the data as and when the nodes which are in sleep mode, they wakes up. So, the AP has more burden, whereas the nodes will save their power. And keep one thing in mind, access point normally runs on not on battery, they may be on running AC power, because they may be fixed on a wall at some place. So, therefore, they are taking the normal supply. So, power may not be that important aspect for AP, whereas this may be very important for the battery operated mobile or portable devices. So, AP can afford to have doing additional work for those nodes which are saving their power. So, therefore, the power management is equally important to know that the node is in this. Now, then more data. When data is transmitting, it is not only the fragments, and the more data frames may be coming. So, one is the data frame which comes into fragments. If all fragments of a data frame are received, then the next data frame may come. So, also it must contain, when a frame transmission completes, whether from the same station the next data frame will come or not. So, this also field will call more data frames, or this is the last frame. Then we have a WEP, which you call wired equivalent privacy. That means, whether this wireless protocol 802.11 is implementing the same security as it is implemented for wired one. That is why it is called wired equivalent privacy. And the last bit is a reserve bit, probably which may be used in future. Now, after having said this, now look at this. How does this control frame FC, and when it is sending RTS, so it has a FC, then it has D. D is duration, and duration will contain that the duration of how long a packet or a frame transmission will take. So, that period must be kept in D. That is why those stations which are not involved in transmission will have to wait. How long they will wait? So, therefore, the duration of the transmission of a frame is kept in this, and this frame will be heard by other stations. So, they know that how long the data transmission will take place, therefore, they will wait for that period and the duration is, and second is this duration also contains the contention free period as well as the contention period information. So, this contains three important fields. D means it contains the duration of the data frame, the duration of the contention free period and the duration of the contention period, so that all other nodes in the network synchronizes with the ongoing transmission. That means, if the contention free period is over, it should be over for all the nodes. They know that the contention free period is over. So, when station transmitting sets the contention period, it must be communicated to all in the network through the D, so that the synchronization is maintained. Now, FCS I have already talked about. Now, this I talked, and look at this YDS and to DS and from DS. So, have 4 combinations, both are 0, one is 0, other is 1, 2 DS is 0, from DS is 1, or 2 DS is 1, from DS is 0, or both are 1 1. So, 4 combinations. So, this address field, if you look at the last one 1 1 1, 2 DS is 1 and from DS is 1. So, address 1 will contain the address of the receiving access point, address field 2 will contain the address of the sending access point, and address 3 will contain the address of the destination device, the station to which the message or the data is being transmitted, it will contain address of that station, and address field 4 will contain the address of the sender, that is source device. That is why the 4 addresses are important. So, from which AP, that is what, from which distribution system is the message, the data is coming, and which distribution system is supposed to receive this data, and within the distribution system which station is supposed to receive, and within the distribution system from which station the message is coming. So, 4 are important, but in the case 0 0, there is a address 1, address 2 is used because it is in the same BSS access point. So, the destination and the source are within the same access point, therefore, you do not need to keep the address of source AP as well as destination receiving AP as well as sending AP, therefore, to DS is 0, from DS is 0, that means it is same, there is no distribution system. But if it comes from some other AP, then the sender AP address is kept here and the source is also a station on that BSS and may be coming to this BSS. Now, after having said this, so what we talked about is the different fields contained in the format of 802.11, and that is how the communication takes place. Now, one of the important point is, if you look at your access point, that your access point is on all the time. When somebody comes with his or her laptop, the moment one puts off a laptop, that it must connect to some access point, so that it becomes part of a BSS. Now, that is what you call association. So, in addition to transmission of a data from a station to other station, one of the tasks to be performed by this AP is also association of a new station to the basic service set. When you put off your laptop, that means you are de-associating yourself as a user from the access point. So, to maintain this information of association with an AP, when you are on joining this network and you are leaving this network, disassociation from the AP. This is one of the management job the AP has to do. But in addition to that, a station may be, the moment you come to a place and your laptop is on and you try to connect to an AP, it may be within the transmission range of more than one access point. That means, there is an overlapping area which is being covered by more than one access point, and you are at the present moment in this overlapping zone. Now, to which AP you will try to connect? Now, either you connect to access point A or you connect to access point B, because you are getting signals from both the AP. Now, that is where the important point is. Now, it either mention or measure the signal strength and do it, and then it must associate or reassociate with one AP. That is how the management takes place. So, this is another task of management of an access point. So, in this lecture, if I conclude it here, what we talked about is, we talked about the working of ANOR 2.11 and how its frame format and how it works in detail. That is what we covered, because this is the most widely used LAN, wireless LAN protocol used in every organization. So, this is what I conclude for today, and tomorrow we will start with wireless WAN, that too is cellular network systems, and next 2 lectures will be on cellular communication. Thank you very much.
So, well friend, I thank all of you for watching the lecture, and on behalf I thank Dr. D.K. Lovial for giving such a wonderful lecture. Thank you very much.